Alright, time for another DraftPhysics.com video presentation. Uh, Mostly. Okay, we'll do the lessons and kind of incorporate into comments that are quick and easy. And so I found this comment. Somebody referenced it. I said, oh, I better go look at that. So Mindless Marvel says, regarding the Walter Lewin clips Gary's played at whatever, ask him about the reverse scenario. One 10-ton train moves and splits into two 5-ton trains. One not moving, one that will presumably gain the energy taken from the one that's not moving. The momentum was the same, but you need energy to separate the two 5-ton trains. So yes, this is almost kind of a fact that I put ink into some fluid and it's really hard to get the ink back out. Really easy to put the ink in, really hard to get it back out again. So yes, when things combine, even asteroids hitting the Earth, it's very hard to put the asteroid back out into space again. It's very hard to put the conditions back into the previous condition, because the natural state of the matter is to mix and not to stay unmixed. And unmixing is not simple. There's no force to allow it. There's no gravity, or there's no adhesions. There's no mechanisms, because it's a push universe, I guess you could say. And there's no way to pull things back out, right? You can push things in, but you can't pull them back out. You have to push them back out. And that's the catch. Okay, but it's not. I have explained ways that you can attempt it. Okay, that seem, yes, you'll get the result, and you won't have broken the energy rules. Okay, of using more energy going one way than the other way. You can reverse it. It's just more complicated. Okay, you can get the ink out in ways that are benign. Don't require more energy. Yes, if you have a Velcro or tape that doesn't stick, you're not going to get an elastic collision all of a sudden. Well, you sort of are, unless you think the Velcro can absorb all of the energy. And if you think it absorbs that much energy, then the fact is when it first hits and then it bounces internally, the little bounces, would be somehow using up all the energy. And so you wouldn't be able to stick two things to each other and conserve the momentum if the Velcro was all of that. I mean, if it was capable of extracting that much energy. And so the energy still has to go somewhere. So you have to explain what got very hot or what did something. You have to explain where the momentum goes. That's the whole idea of conservation laws. So, the burden is on you to defend your position, that somehow all the energy disappeared, and you have to explain where it is. Most collisions in real life are partially elastic. Yes, we don't have any ideal experiments. We only have the flawed ones we can do here in the circumstances where air can be humid and lots of things can be shitty. But we can imagine them in space if the NASA won't do them. NASA should have done all these experiments, right? I mean, they're not very complicated. Let's put some springs on stuff and shoot it back and forth between that little army thing they have on the shuttle. They could do lots of experiments that they never did. And they probably have done them, frankly, and we just didn't get a report on it because they did them accidentally. All the time they have to launch things off of their shuttle, and they use springs and different mechanisms to push them away and blah, blah, blah. So they know some of this stuff already. Apparently, minimizing surface area of contact is important for elastic collisions. I don't know where you got that from. I have no idea where you got that from. Whether I put a little tiny steel pointer on the carts or I have them hit on a flush surface, where did you prove that makes any difference? Where was it demonstrated that makes any difference? If you see Lewin's video, the carts for elastic collisions had elastic bands for bumpers. Yeah, that was to make them super elastic. He said the extra words. Because frankly, the experiment isn't very doable, I would say fakeable, without the spring. I mean, unless you think the spring actually carries enough momentum, its movement, that somehow it is creating your extra energy. I think what the springs do is cause the carts to lift and do things that, create the extra energy because of the airflow. So the springs are complicating the experiment. It's a variable. It changes how the carts react to the collision. I would say an obvious difference between the two collisions is the collision is less fast. Steel on steel is very fast. Steel on spring on steel is much slower. I initially thought Lewin was being sloppy here, but actually this can be made to make sense. It's an idealization, of course. I don't even know what you're talking about in terms of, I think it was sloppy in that Wise's cart got a whole bunch of clay smeared all over it. Hint, the relationship between Ke and momentum is K equals P squared, so the momentum squared, which, just now we're really getting silly, divided by 2m, the mass of the wall. Obviously, there's a point where the wall becomes immovable, and it doesn't matter what mass it is. So by this equation, if I had the Empire State Building versus, some much smaller building, a house, common house, and I throw the tennis ball against the two, I'm going to get a different answer. The tennis ball is somehow going to know I hit the Empire State Building rather than, say, a brick house. No, it's not going to know the difference. So the equation fails in all respects, in the sense that the mass isn't going to matter. The mass can't really be that relevant, because there's just a point of moving and not moving is the real relevant point. You're either giving the energy back or you're not. Alright, so that we'll talk about. And I will draw a little bit. And then we'll do other subs. So entropy's coming up. I'm going to probably play some Veritasium. I haven't seen the video yet, but it relates to another comment that we'll finally get to eventually. And hopefully I can get all that done in this video. Or not. I'll just make another video. Okay, so as stated, in a push universe, it's very easy for this to happen. One thing to bang into another thing. Oh, this could be better. Yep, it could be. Yeah. Well, anyway, so this has motion, say 10v. Okay, let's say it weighs 5. Alright, crashes into another 5, and this can happen. Pushes, they combine, they merge essentially, and this experiment has been done quite successfully, and you get just about, you get a 10, alright, just about going 10. So let's just say 9.8. You conserve most all of the momentum, and that's the result you get. Now the tricky part is, how do I go from the other way, 10, and then I lose 5? Because then I have to add energy. I can't just bang them into each other. So it's sort of the ink problem. Well, what I've suggested is that you can have the 10, created in a way that allows that. So if I create the 10, alright, by first loading it, with the 5, that is, I'm going to drop the other 5 on top of it. Alright, so it's going the 10 velocity. Alright, I'm going to merge the two, but I'm going to merge them conserving the energy I used for the merger. So this time I'm going to put a spring on here, and I'm going to catch this object with the spring. So when this gets merged into this, it's going to catch it with a spring. It's going to bang into it. The object's going to compress the spring, and then we're going to lock the spring. So now I have, a 5 ton going 10, and I have a loaded spring because the spring hit the other 5. I compressed it, so I have the energy that it took to absorb the other object and merge it. This is a 5 mass. Alright, so now I have my 10 mass, but now I have it. And so all I have to do now is rotate that. So spinning the one mass on top of the other isn't that much energy. But yes, I do have to rotate it. Okay, and if you get my drift, what I'm going to end up doing is I got a 5 mass on here. I have my spring. Okay, I have my 5 mass here. Alright, and basically I'm just going to slide it off. Okay, with the spring. I'm going to release the spring. This is going to go back to being 0, because it's the same energy that took when it absorbed it, same velocity. And I'm going to end up with my 5 going 10 velocity. And yes, there'll be some losses. I'm just saying it is a way of conserving the merger energy, okay, because the merger energy really is just incidental. Just because it is a push universe, it is a mixed universe, it's not an unmixed universe. It's harder to break things apart than it is to put things together. Just the fact of how the universe works. One thing is more complicated than the other thing. Alright, so that takes care of that. I believe it takes care of that. I mean, the simple truth is that you can see how the fact is that yes, the energy it takes to move the 5 off is exactly the energy that restores the velocity to the 5 mass. It's back to 10 again. So it's in there. It's not magical. Alright, pause. Alright, so a related subject is this brought up by Piro in kind of the usual kind of a lies way. In Draft's answers to this video, he actually explains, well, what I actually explain is that his response isn't a response to anything I'm saying. He's not dealing with the 9.8 meters per 1 second fact. That he's not really dealing with the fact that it's twice the velocity, twice the weight, twice the time, and you're saying that all those 2's add up to a 4 somehow. Okay, what you were trying to tell him, okay, in the last video about the spring moving towards the lighter object from here. So again, I never said that springs don't move their center of mass. I've talked about it before. The center of mass is sort of a real thing. But the point is I don't think there's any set rule for this, at least one that you know, okay, moron. So, talk as if you know something when I don't think you do. So, now the problem is this other, who apparently is an 80-year-old guy who should be in the Chappelle Natural, soon-to-be-dead society. I'm sorry. I mean, being 80 must absolutely suck. But anyway, it doesn't really give you latitude for all of this crap. But anyway, it doesn't. We'll get to the subject. So there's this, it's a simple argument, right? Okay. It's a simple. All right, pause. I have to get a new marker. All right, we're back. It's a good thing I got a new marker because I didn't realize I had the thing in the way. Anyway, all right, this one's close enough. All right, so the whole argument is, okay, so we know in the Newton's cradle I hit equal mass and equal mass, and I perfectly exchange the energy. It goes into this object, okay? This object stops, this object goes, everything works just fine. And then now the complication gets into, what if I start making this bigger and bigger and bigger, right? So the thing I'm hitting gets bigger and bigger and bigger, and that's not that much bigger. So anyway, well, try to be more realistic. That's not that much bigger either, but you get the idea. You can get the idea that I'm saying it. Okay, we'll just make this smaller and then you'll get the idea. Alright, so I'm swinging this side in, and I'm going into a bigger and bigger object, and there's this point where they say, okay, that I get to this immovable, okay? So this one can't move. Alright, and I hit into it, and now somehow I have 2x the momentum in here. Okay, so somehow I'm taking 100 foot-pounds, and now I have 200 foot-pounds in here, even though it's not moving. And that here I have 199. Here I have just 100. Okay, 100 in, 100 out. And somehow as I increase this mass, I go from 100 to 200. And I'm saying, but there is no rule for that. There's no law for that. There's no mechanism for that. And where's the transition? So either this happens, this 199, where I make this move just a little bit, it absorbs something, and I start diminishing this as reflection. So let's understand, I get 100% reflection here. Now tennis balls are only 75% efficient, so they're a pretty bad example. So you have to use like a hard rubber ball or something just to, hopefully make the experiment work better. And their argument is that I start getting less reflection as this yields, but I still have more momentum going this way. So that's the complication in this story. Is this real? Okay, is there free momentum, the Lewin experiment, real? Is that phenomenon real? All right, I'm arguing that I tend to think not. Certainly tend to think not. Until I see some really good evidence, because it doesn't make any sense. It's not conservational at all. There is no putting a 1/2 and a square on momentum. That's what the kinetic energy formula is. It's momentum at its core, and all they've done is this nonsense. Okay. Now that trivial extra mathematical figures are not real things, as I pointed out. And how do they turn it from a scalar from a vector into a scalar? This is a vector. It has a direction. All of a sudden, this 1/2 and square, we're supposed to believe now it doesn't have a direction, and now it can't subtract. I'm saying bullshit. All right. Anyway, so yes, the simple argument is there's a point in this transition where you have to sort of concede that this doesn't have 2x the momentum. It's not moving. I mean, it's kind of silly to say it has momentum when it's not moving. It didn't move. There's no evidence that the momentum is anywhere, that it's doing any moving. So why are we saying it has twice the momentum? How can it have the velocity when it doesn't have any velocity? That's a zero. M times zero, zero, any number times zero is going to be zero. It has zero momentum. All right. And so the question is that in the spring's compression between these two objects, and now it's going to expand. And the fact is if I put a very light object on, so if I make a big comparison, big difference. See, these differences aren't huge until you get down here. Then you're getting to maybe a 10-to-1 difference. Okay, in terms of the masses. This one might be 10 times more massive. But the rule is going to probably be you're probably only going to have to get half as massive. 5 times as massive. Who knows what the number is? That's what my argument. What's the number where all of a sudden, when the spring expands, it's going to expand so much easier in this direction that it can't do much pushing in that direction, because it's going to use up its energy long before it can accelerate this object. It accelerates the heavy thing very slowly. Okay. All right, very slow acceleration here, very fast acceleration here, and the more that differential happens, the more the spring will have used all of its energy moving the fast object, because it happens so much quicker. And because the slow object requires you to push on it for a while to get it going, it takes time to move it, more time to get it going, then yeah, it's going to be out of luck, because all the energy of the spring's center of gravity will have moved. Now I've used this in the gun analogy because it's an interesting question, how much of the gun, is about the explosion taking place. Now you have 1,000-to-1 relationship between the bullet and the mass of the gun. So it's 1,000-to-1. This is 1,000 atoms, this is 1 atom. And when the explosion takes place, now the difference is this ain't a spring. This explosion has bits moving insanely fast. And the question is, basically, if I don't allow the gun to recoil, that is, I lock it down really tight so it can't move, it can't yield, does the explosion actually move in the direction of the bullet? Because the explosion is taking time too. It's very, very fast, but it does take time for it to explode, to finish. Okay, and it's creating all kinds of different particles, electrons, heat, all kinds of different stuff is flying out of that explosion. Atoms and then little bits of carbon and all kinds of different things are flying out of the explosion that are going to be transferring their momentum. And the question is there any possibility of the energy actually reflecting off the gun and going into the bullet, increasing the bullet's energy? Or will the explosion actually itself move forward a little as it's exploding, because it can't, the gun isn't yielding, so it's reflecting the energy, and their energy is pushing the explosion forward. And so those are all open questions. Now, I would argue that it does make a difference, that if you do tie the gun down, you'll get a faster bullet, okay, than if you just let the gun sitting on a table and you just fire it electronically, and the gun is free to move, that you will get a higher muzzle velocity, okay, from the gun, from the bullet. Where you get a higher velocity period from the bullet if you tie the gun down. And if you don't tie it down, you get less, because there is some movement. But I'm just saying, you don't have any formula for that. There's no Hooke's law for this that explains exactly when this is way too heavy and that's light. So there's no space analogy for, throwing the rubber ball at the Empire State Building in space. A big, giant, massive object, I throw the rubber ball, okay, versus 10 pounds, and the ball is a few ounces. I'm going to argue that it's not going to matter. 10 pounds, Empire State Building, I'm going to get the same bounce, because the differential between the masses is high enough. And once you're high enough, it doesn't matter whether it's the Empire State Building or 10 Empire State Buildings, I'm going to get the same bounce, which is going to be near 100%. And there's some point where I hit that 100%, when I'm getting all the bounce I'm going to get. I'm not going to get any more bounce. I'm just going to get all the bounce I'm going to get. So there's no formula that tells you when this moment happens, where the object's big enough that it's going to move so much slower than the other object that as the spring expands, it's going to expand in the direction of the lighter object. The center of the spring's mass will in fact move in the direction of the lighter object. So I'm saying that's unfinished, incomplete physics. Okay? I'm not arguing it doesn't happen. I'm arguing you don't have any rules for it. And in the context of the lack of clarity you have in this free momentum idea, this free momentum experiment is so sloppy in terms of it, any definitive truth being gleaned from it, that until you establish that as an actual truth, that you can actually create extra momentum in a direction, it's a little bit moot to have the conversation. And clearly in the Lasco video, I was clearly arguing the arguments I am making. Now, he's pointed out that he doesn't believe in conservation of momentum. He doesn't think springs conserve momentum. So that's a much bolder statement, and one I don't think he can defend with any evidence. So let him produce something called a piece of evidence. If he's going to claim it takes 4 times the fuel to go twice as fast, prove it. If you're going to claim you don't have to, if levers don't conserve momentum and springs don't conserve momentum and none of these things, then prove it. Show the experiment that demonstrates some inkling of that being the truth. And then I'll point out how the experiment's a piece of shit, frankly. Anyway, I think that covers it. Alright, so there are these, 9 comments by this. I mean, obviously it's nice that he's interested in the subject, but he's old and doddery, I guess, and too stupid to figure out something I've made clear over and over. So I clearly just made a, off the top of my head example, just to prove a point. Okay, and the simple point I was proving, we'll go back to the drawing board, was that the gravitational influence, gravity is not producing all this tremendous amount of energy, this squared function is crap, because the distance, especially in the context of anything called distance, okay, and it's just about time. And so I've made this argument over and over and over again, and it's not getting countered by any of these J.O. crap or whatever his name is. Where's your counter argument? Okay, the faster I go through this amount of distance, let's just say we care about this distance, and there's going to be an amount of gravity created in that distance. The Earth has an influence on this satellite I'm shooting. The absolute fact is that it's the same amount of distance. All right, and the slower I go, the more likely I crash into the Earth. The faster I go, the less and less I get deflected. Okay, tiny deflection if I'm going fast. Okay, just tiny. Right, and the deflection is a measure of falling. It's the same as falling. It's just showing you how far you're going to fall in so much amount of time. The influence of the gravity. And so I could just use the speeding bullet argument. Okay, the bullet across the surface of the Earth. Okay, yeah, it goes this huge distance, but it only is affected by the amount of time. And guess what? It falls at exactly the same rate here as it did here, the same time it hits the ground. It did this gigantic amount of distance in the gravity, but it doesn't matter because the amount of gravity that affected it was exactly the same, because it's the amount of time that matters. So it's all over the place that all that matters is time here. Distance is silly. So I made an example. If here's the Earth, here's a certain distance, 40 miles away. I have something flying very fast already, say going 2,000 miles an hour. I think I said 20,000, yeah. 20,000 miles an hour, and I didn't know this on the top of my head, you fucking idiot. You're 80 years old, and you know that nobody knows off the top of their head how long it will take something going 40 miles at 20,000 miles an hour. And so I guessed, I said, let's just call this 1 second. Just for the sake of the argument, we'll call that 1 second. So it gets 1 second worth of gravity. So I said, what happens when it hits the Earth? Well, instead of going 20,000 miles an hour, it'll go 20,009.8. Yeah, that's all that's going to happen. It's going to go through 40 miles of gravity, 40 miles of falling distance, and it's only going to get 9.8 added to its velocity. That's all the energy it's going to get. So 40 miles of going in gravity is going to equal 9.8. Now, obviously, by your dopey, MGH kind of nonsense, okay, you say that this somehow has this giant potential because you're going to count every one of these feet as the same amount of energy, no matter how fast you're going. And they don't have the same amount of energy no matter how fast you're going. So that was the simple argument. It was just to illustrate that it's kind of silly to talk about it being anything meaningful in any other context than time. It's a time-dependent force. 9.8 meters per 1 second is the ratio. That's the truth, okay? It's not per 1 second squared. It's not per seconds squared. It's per 9.8 per every 1 unit of seconds. And then you multiply that times how many seconds you took. 4 seconds, let's say. Then you find out exactly what your velocity is going to be and exactly what your momentum is going to be. And there's no room for any kinetic energy nonsense anywhere in there. That you're not going to dispute. Anything said in this section you're not going to dispute, all right, with anything rational, because it's the absolute truth. How much the gravity affects you is completely dependent on how long you're in it, free falling, period. Not how far you travel. All right, so now we'll go back to the regular comment section, I think. I mean, there's no... See, right here he says, of DS Lay's video, I was making it up. Yeah, I was just using an average kind of approximation, an illustration, for illustration purposes. And it wasn't even that far off, right? The difference was he calculated it to be exactly 2-point-something seconds. So, yes, my turning it into 1 second, I should have made it 10,000 miles an hour, then I could have said it was 1 second. I mean, this is how anal and, butt crooked these people all are. All right, so I will read this other piece of shit comment from another shithead. He doesn't care to know about the truth. So this is like just exactly what a Christian could say. Oh, he doesn't care to believe. He doesn't want God's love. I mean, this is so pathetic. He only cares about to own the truth. Well, if you don't really want to own the truth, that is, you don't want it possessing you, then you got to be in the wrong business. I want to own the truth. I want it to possess me. Okay. Your every attempt to convince him. So this is the bullshit. Your every attempt. Where is your attempt? In fucking 350 years, you can't produce one single experiment demonstrating it takes 4 times the fuel to go twice as fast. Not one single experiment coming close to proving that or demonstrating that. Not one single one. And I can make simple thought experiments that completely defeat your notion that this has something to do with distance. When, yes, it has everything to do with time. How much paint gets on you. You're standing in front of a paint sprayer. How much paint gets on you is completely dependent on how fast you travel in front of that spray. And the faster you travel, the less paint that gets on you. And distance is moot. Okay. I mean, amazing. Every attempt to convince him with the completely non-existent experimental evidence. I mean, you're just a religious kook. Saying, well, why aren't you paying attention to the revered word in our Bible? We don't have to have proof or evidence. It's going to be futile. Okay, convince him is going to be futile. Yes, okay, it's futile in this circumstance. You don't really give a fuck, right? The loser is the guy who says this, by the way. 8,159. Typical loser rhetoric, frankly. Okay, so there's a bunch of little mindless marbles mush here. 30 minutes into Gary's response video, and he is not even following anything said in the video. Yes, because his response video isn't a response to a fucking single thing I said. Unlike the courtesy I pay these people, I play their video and respond to it. They won't play my arguments and respond to my actual arguments. Instead, they make up some other subject and decide to talk about that. Where have you in any way addressed the fact that in 350 years you have no physical evidence that it takes 4 times the fuel to go twice as fast? You won't even admit that, damn, that's just fucking weird, isn't it? That in 350 years we can't come up with one example demonstrating that decisively? It's a fundamental truth. It's a fundamental experiment done every fucking day. Every day somebody hits, high speed, going from medium to high. Every day people are hitting these buttons that are doing this, and you don't have any recorded evidence. Oh. Gary cannot follow any reasoning whatsoever. Yeah, whatever. I followed the reasoning. This is just your silly interpretation. I played his fucking video and responded to the points, so fuck you. You're such a despicable liar. Let's see. Leska is discussing the conventional definition of force versus impulse. What conventional? There was Newton's definition. Clearly he agreed that Newton made it pretty clear what he was saying. Twice the force, twice the speed. Okay, not complicated. So, and you're saying that that's broken, and he didn't explain why that's broken. He didn't explain why we have to fix that, because that's silly. Where was his explanation that that's a silly theory? I mean, it's silly, incomplete, completely not right. Where did he explain that anywhere in the fucking video? Oh, that's right, absolutely nowhere. He just wants to play this middle-of-the-road mushy game that somehow this is a semantics argument, that MV and momentum are really the same thing, they're completely compatible. Yeah, even though they get completely opposite answers. I mean, you people are so full of shit, it's just amazing. And Gary thinks Leska is talking about kinetic energy. The subject is kinetic energy, frankly. It's the versus thing. Versus is in the titles. Clearly that is the subject. He's changing the subject. I'm not changing the subject. I want to talk about conservation of momentum versus conservation of kinetic energy, because whatever one is conserved is the one that's real. So if you can't figure that part out yet, you're pretty goddamn stupid. Seriously, what even is the conversation. You can't figure that out yet, huh? You say they're compatible theories, that somehow you can have a notion of momentum and it can mean anything at all in your kinetic energy, fakey, phony world. I'm arguing plainly, it can't mean anything. One of them is nothing and one of them is something. There's absolutely no way that they're compatible. They get completely different answers to simple questions when it comes to trying to conserve this crap. You can't conserve both in most interactions that take place in the universe. All right, and honestly, so he couldn't do this as one comment. It's just downright disrespectful, which is not new. Gary complains people are not on the subject, and yet, just like his other accusation, he is 100x worse at staying on the subject. So he calls it downright disrespectful. I played his fucking video. Where did he do me that courtesy? Where did he show me any respect and actually deal with the arguments I was actually making? The actual arguments about conservation rules. Can a spring produce different amounts of fucking momentum? He says it can. Okay, I put two heavy things on the spring, I'll get a different momentum number, more, ironically, and to some extent my entertainment, that they actually believe I can make more momentum by putting two heavy things in between a spring and pushing them. So the heavier they get, the more momentum I create. And the lighter they get, the less momentum I create. That's their ironic, insane logic. And this guy sits there and ridicules my logic. Amazing bullshit. I mean, how despicable a creature are you to type this absolute bullshit? You fucking lying piece of crap. I mean, damn. Amazing shit. Alright, this is another Puro. That was I already read. Okay, so let's go to the regular comments now. Alright, so the entropy subject will come up. So that will be good. Alright, force is proportional to change in momentum. So this is the 80-year-old guy. This is just word mush. Force is proportional to change in momentum. What does that mean? I mean, obviously in the subtext, Newton made it clear. It's not proportional. It's equal. You want to go twice as fast, apply twice the force. You want to go 3 times as fast, apply 3 times the force. That's not a proportionality. That's a direct equality. Which is the difference in momentum. Yeah, obviously if you change the velocity, you're changing the momentum. That's proportional. So as long as the mass stays the same, it's a direct equality. If the mass changes, well then obviously it's not a direct equality anymore. But clearly if the mass stays the same, you have a direct equality. Okay, which is the difference in the momentum of an object between two distinct time values. It has absolutely nothing to do with it. It doesn't matter whether the acceleration happens in a half a second, a millisecond, 2 milliseconds. It doesn't change anything. The fact is, it's a change in the outcome, what it's going to have when it's done. It's a net effect. The net effect is you've changed the object. The net effect after 1 second in gravity and free fall is that you're going 9.8 meters per second. Now, as I pointed out, you only traveled 4.9, so your average velocity isn't anywhere close to that. But the fact is that the velocity you reach after that, you're at 0.999 seconds, okay, and you haven't quite got there, but at 1 second you're at 9.8. So this is just baby talk, frankly. This is such trivial crap, and that is not the same as the momentum value centered at only one particular instant of time. So again, none of this has anything to do with any particular instant of time. It has to do with the end product after 1 fucking second. That's the ratio. Now, if you want to make it a half second, then we have to change the 9.8. You want to make it a millisecond, then you have to change the 9.8. And you already know that because you did these wacky calculations that, per hour, you're getting, whatever, 268,000 miles per hour. Yeah, but it's Fine, you can do that. That's a real formula. That's a real ratio. The ratio changes if you're going to change the units. So, but we already know we don't need to change the units. The units work. These units work fine. So you're just so full of shit. That this is a nothing statement. It's not saying anything. The point is where do I have any reason to square the fucking velocity? Why would I square the velocity and think that's a real thing that's happening? Because it's going 9.8 meters per second, that somehow, no, it's really going, 100. No, it's not going 100. It's going 9.8 meters per second. All right. I am over 80, and I know what I said above is true. Well, spoken like a true Christian. You know it. Yeah, that impresses me. I mean, saying you're over 80 isn't going to impress anybody, frankly, especially if they have watched the John Chappelle Society thing, because, yes, they're all nuts. Religious nuts, too, most of them, which is even worse, pretending to be scientists. So, fuck you and that. My condolences. I mean, I'm sorry. Must suck being 80. Regarding the comment, which I thought may have been held for review. Okay, so we don't even have to bother with that. Yes, YouTube sometimes blocks comments for no good reason. All right. So he does it again here. Explanation. I was making it up. Yes, I was using it as just an example. I wasn't making some authoritative statement that 40 miles from space at 20,000 miles an hour is only, 2.7 seconds. I wasn't making any assertion. I was trying to just make an illustration that the contribution gravity makes, even though it's 40 miles of gravity it's going to go through, it's going through 40 miles of gravity, but all it's going to get is 9.8. Because that's all the time it was in the gravity. That's all the time it could be in the force of collecting the force. And that's all it's going to get is 9.8. You can't... I mean, it's almost like I'm saying you people can't be this stupid, but apparently you can be. Alright, so now to the subject of inertia in a way. Not inertia, the subject of entropy. I'm sorry if I said it misspoke earlier. Okay, so hi DS. Are you saying that momentum particles become trapped? I don't know if I want to call them momentum particles, but yes, force. Okay, let's just call it force. Bits of force. Trapped from the internal pressure effects of gravity on a mass, especially a planet-sized one. Yes. To create gravity, you have to take the Earth out of its equilibrium. That is, the Earth can't reflect absolutely as much as it absorbs. So stuff goes in, but not quite the same amount comes back out. That's what has to happen. And the heat of the Earth is evidence of that happening. That's the energy differential. Within matter and manifests itself as heat. Yeah, I'm saying the side effect of the absorbed force is momentum given to particles, and that momentum is real, and it's taken from the universe. If so, can that explain the origin of the intense heat at the core of the Earth? That's the whole point. Yes, the bigger the object gets, the hotter it gets just from gravity. It doesn't need any tension between other gravitational bodies. It doesn't need any other thing pulling on it. The fact is, creating gravity will make heat. Now, in small objects, it's going to be a minimal amount of heat, but obviously the bigger the object gets, the more gravitational energy it's creating, manifesting more and more gravity. Therefore, it's going to collect more and more heat. In essence, large masses converting gravity into heat. They're converting the pressure on the outside into internal pressure. You could look at it that way. And so thereby consuming pressure. So you could make a conservation of pressure argument, you can make a conservation of temperature, you can make a conservation of a lot of things. But the fact is, the fact that the Earth has sequestered some portion means that it isn't at equilibrium. And likewise of the sun, with gravity rather than nuclear energy powering the stars. Yes, the massive sun is under intense pressure on the inside because it's constantly absorbing some of the energy going in and converting it into heat, and then it's always behind is the subject, so it radiates the it has to be in the long term at equilibrium, but in the short term it's always behind. It's sort of the argument. It's always a little tiny bit of energy actively working in the earth, and therefore it's not energy on the outside pushing in. Okay, and likewise, yeah, so yes, to me it's a reasonable explanation for why the core of larger objects gets hot. Okay, so now to the entropy argument by Veritasi. No, yes. Ugh, boy, what a mess of commercials. Yeah, I couldn't even start it from the beginning because they just kept replaying the commercials. So, anyway, I think the volume is probably got to be, well, we'll see. So this is a video, he says, right? So this is a video about one of the most important, alright, so we'll take the captioning off.
About one of the most important, yet least understood, concepts in all of physics.
So I'd say sort of bullshit, okay? It's not all that important or all that interesting, frankly. So, whatever.
It governs everything from molecular...
So it's just more bullshit that this is what governs. Momentum is what governs. So if you want to do this idea of the most important subject in physics, it's that it's a momentum universe, a push universe. And every single thing that has a velocity vector is going to bang into something inevitably. And when it does, it's going to transfer that momentum, and that's the cycle. We're just watching. It's as if there is a little substance, and this substance has been in the universe forever, and it just keeps moving to all kinds of different places. And it'd be really cool to be able to see that. To be able to see these illustrations of, let's just isolate one piece through billions of years of transition through the universe. To me, that's very interesting.
Collisions to humongous storms from...
Right, butterfly effect, blah, 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 blah. Little tiny things making for, the tipping point. The one little tiny pea that made the difference and made the boulder fall down the cliff today rather than 5 days from now.
The beginning of the universe through its entire evolution.
La 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 la. So he's just making whatever slopamentaries now. This is just, all of this is just such wooey little. Once you feel God's love will love you. This is just mush.
To its inevitable end. It may in fact...
So it says you, right? So they don't have any real evidence it's going to inevitably end. They don't have any real evidence the universe is expanding. They don't have any real evidence galaxies ever do anything but just keep doing what they're doing. Getting a little bigger, getting a little smaller, getting a little bigger, getting a little smaller.
To determine...
Never saw a galaxy supernova, right? They can merge, but we've never seen one blow up.
The direction of time and even be the reason that life exists.
Oh, now he has to throw life in there and the reason why life exists. La 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 la. What a big pile of hypey crap this is. Oh, puke. A half an hour of this crap? Amazing.
To see the confusion around this topic.
Oh, well, it's confusion. The confusion is that science says something really stupid. Entropy's a real thing. Well, except when it doesn't happen. So except for the parts that are where stuff is sticking together, everything has to fall apart. Except where the stuff is sticking together.
You need ask only one simple question. What does the Earth get?
What the fuck am I doing on this planet of shysters, crooks, fucking bums, retards, morons. Why the fuck am I on this stupid planet of stupid creatures? It's the only question I need an answer to.
Get from the sun.
The sunlight, okay, that's what it gets. It also is being tugged by the gravity, which is heating it internally. But, the part that they're not going to talk about is, well, obviously it's getting a lot because over the last, 300 million years, we stored a ton of solar energy in coal and oil and other hydrocarbons that are trapped under the crust of the earth. And all of that crap we took from the sun. All of that complexity.
What does the Earth get from sun?
Well, it's light rays.
What do we get from the sun?
Heat. Warmth.
Light.
Vitamin D, we get
So the catch is he's going to try to say, well, it's all at equilibrium, right? The same amount of sunlight comes in, the energy has to be released or the Earth will get bigger and bigger and bigger. So it has to be at equilibrium. But the truth is no. For 300 billion years, we weren't at equilibrium because the sunlight would come in, it would hit the plants die, they rot, they go into the ground, and they stored all of that energy. So it's a tremendous amount of energy. Millions of years of solar energy are what oil is made out of.
vitamin D from
Would you get vitamin D from the ultraviolet rays?
Well, it's a lot of energy.
What does the Earth get?
So we obviously don't get vitamin D, so that's another, but that's like the hydrocarbon, that's like storing the energy. The energy hits and it makes molecules into molecules that contain more energy. They can release energy.
From this energy?
Yes, energy.
Energy.
Motion, momentum. They can release momentum. You can make electrons and protons move.
Nailed it. Every day the Earth gets a certain amount of energy from the sun, and then how much energy does the Earth radiate back into space relative to that amount that it gets from the sun?
Probably not as much. I don't believe that it's just radiating right back.
I'd say less.
Less. I would
Less.
say less.
I'd guess about 70%.
I think it's a fraction. I'd say 20%.
Because we use some of it.
We use some of the energy.
We consume a lot.
So the point is use just has to do with, again, it's transition. You can never kill the energy. So yeah, you can use it, and then you can use it here, and then you can use it here, and then you can use it here. So if the energy comes in as little, the most discrete amounts, in the most discrete form, then obviously you can use it by storing it. So this is really just a conversation about storing the small kinds of energy. And then you're storing it in big clumps of matter, and you could break the big clumps of matter and release the little bits that were stored. I mean, it's really not that complicated, but there's no law that energy won't clump. And the only law there would be is if it was really a light bulb, and there was a big bang and it was a light bulb, and it just meant the light shot out. Well, there's no way for the photons to hit each other. So there's no way for them to do anything. So unless there was a bunch of matter out here somewhere for the photons to hit, it wouldn't make any difference. There has to be some clump. There has to be a clump to collect. And we know that the matter clumps. So whatever matter there is, we know it has a force that's an anti-entropy. There's a force called gravity, and the force of gravity is going to make the stuff clump. It's going to make it become bigger. And bigger means more energy. Storage of momentum.
Right?
But the thing about energy is it never really goes away. You can't really use it up.
Right, there you go. So that's true. You can only store it. Well, you say the word store. That will be the interesting thing.
It would have to break even, wouldn't it? Same amount, yeah.
Cause and effect, it'd be...
So obviously it's not the same amount, right? So as we're burning the fossil fuel, we're not at entropy with the sun, right? The sun's hitting us, the light and the energy is radiating, but we're adding a whole bunch of 300 million year old energy. We're throwing back, reflecting sunlight that hit the Earth 300 million years ago. So when your car is going down the street, you're excreting heat. Okay, that's 300 million years old.
Equal in some ways, right? For most of the Earth's history, it should be exactly the same amount of energy in from the sun.
It should be. So yeah, by what law, right? So obviously this planet is covered with stuff that changes and moves and does stuff, and all that, all the clouds movement, all this stuff happening, all has to be using some sort of energy at the time it's doing it. So it is actively doing stuff. So there has to be some point where you said somewhere it didn't give back, somewhere it absorbed and it kept. And that's the argument, that it keeps a certain percentage for a certain period of time and then gives it back. And that deficit is real.
As Earth radiates into space.
Wow.
Because if we didn't do that, then the Earth would get a lot hotter. That'd be a problem.
That'd be a big problem.
So if that...
So we know that over the past 300 million years that the Earth has actually had that deficit, that a tiny fraction of the equilibrium has been broken, and we stored a whole bunch of heat in the form of chemicals that had to be made with heat, and that chemicals that when you break them apart again, they'll release the heat.
If that is the case,
Yeah.
then what are we really getting from the sun?
That's a good question.
It gives us a nice 10.
It gives us a nice 10. I love it. We're getting something special from the sun,
I don't know. What do we get without the energy?
but nobody talks about it.
Time, it's the time is all we're getting. We're getting the ability to use the energy that has been thrown at us for a period of time, and then we throw it back.
To answer that, we have to go back to a discovery made 2 centuries ago. In the winter of 1813, France was being invaded by the armies of Austria, Prussia, and Russia. The son of one of Napoleon's generals was Sadi Carnot, a 17-year-old student. On December 29th, he writes a...
His life sucked, frankly. It all went to hell. He died of cholera on some stupid island. I mean, these are all such sad stories.
letter to Napoleon to request to join in the fight. Napoleon, preoccupied in battle, never replies. But Carnot gets his wish a few months later when Paris is attacked. The students defend a chateau just east of the city, but they're no match for the advancing armies, and Paris falls after only a day of fighting. Forced to retreat, Carnot is devastated. 7 years later, he goes to visit his father, who's fled to Prussia after Napoleon's downfall. His father was not only a general, but also a physicist. He wrote an essay on how energy is most efficiently transferred in mechanical systems. When his son comes to visit, they talk at length about the big breakthrough of the time, steam engines. Steam engines were already being used to power ships, mine ore, and excavate ports. And it was clear that the future industrial and military might of nations depended on having the best steam engines. But French designs were falling behind those of other countries, like Britain. So Sadi Carnot took it upon himself to figure out why. At the time, even the best steam engines only converted around 3% of thermal energy into useful mechanical work. If he could improve on that, he could give France a huge advantage and restore its place in the world. So he spends the next 3 years studying heat engines. And one of his key insights involves how an ideal heat engine would work, one with no friction and no losses to the environment. It looks something like this. Take 2 really big metal bars, one hot and one cold. The engine consists of a chamber filled with air, where heat can only flow in or out through the bottom. Inside the chamber is a piston, which is connected to a flywheel. The air starts at a temperature just below that of the hot bar. So first the hot bar is brought into contact with the chamber, the air inside expands with heat flowing into it to maintain its temperature. This pushes the piston up, turning the flywheel. Next, the hot bar is removed, but the air in the chamber continues to expand. Except now, without heat entering, the temperature decreases, in the ideal case until it is the temperature of the cold bar. The cold bar is brought into contact with the chamber and the flywheel pushes the piston down, and as the air is compressed, heat is transferred into the cold bar. The cold bar is removed, the flywheel compresses the gas further, increasing its temperature until it is just below that of the hot bar. Then the hot bar is connected again, and the cycle repeats. Through this process, heat from the hot bar is converted into the energy of the flywheel. And what's interesting to note about Carnot's ideal engine is that it is completely reversible. If you ran the engine in reverse, first the air expands, lowering the temperature, then the chamber is brought into contact with the cold bar, the air expands more, drawing in heat from the cold bar. Next, the air is compressed, increasing its temperature. The chamber is placed on top of the hot bar, and the energy of the...
Well, anyway, I thought this was more than this. Oh, okay, so it's really, yeah, it's interesting, but, again, he's really not showing how those cycles are caused by the momentum often of the system. So the system is forcing, okay, the event, and so that's why, like, heat pumps have to use Freon or some compressible gas and all this kind of crap, and it's not quite this simple, but whatever. I don't know how far to go with this. I mean, it's detailed, but not detailed enough to be usefully detailed.
Flywheel is used to return the heat back into the hot bar. However many cycles were run in the forward direction, you could run the same number in reverse, and at the end, everything would return to its original state, with no additional input of energy required.
Except to keep changing the temperature of your bars. You have to make your cold bar cold again. You have to make your hot bar hot again. Blah, 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 blah.
So by running an ideal engine, nothing really changes. You can always undo what you did.
Whatever that means. You can't have all of this motion, okay? The motion has to go somewhere, so you obviously have to put motion into the bars. So as you're using the bars to change the bar's temperature, you have to put the bars back at their temperature. So that's what the cold water and the steam engine is for.
So what is the efficiency of this engine? Since it's fully reversible, you might expect the efficiency to be 100%.
Whatever that would even mean, but fine, whatever. I mean, efficiency just has to do with how much leakage is going into all these other parts and whether you're heating them. So, yes, it could be 100% efficient if we've gotten rid of friction and all this other stuff, but obviously you have to put energy in.
But that is not the case. Each cycle, the energy of the flywheel increases by the amount of heat flowing into the chamber from the hot bar, minus the heat flowing out of the chamber at the cold bar. So to calculate the efficiency, we divide this energy by the heat input from the hot bar. Now the heat in on the hot side is equal to the work done by the gas on the piston, and this will always be greater than the work done by the piston on the gas on the cold side, which equals the heat out. And this is because on the hot side, the hot gas exerts a greater pressure on the piston than that same gas when cold. To increase the efficiency of the engine, you could...
I don't know if that's true, frankly. That the vacuum you're creating, essentially, is weaker than somehow the pressure you created up. That somehow the vacuum pressure is lower than the heat pressure. I can't say that isn't true, but that's just him saying so. That's a statement. I don't know if there's any evidence to prove it.
Increase the temperature of the hot side, or decrease the temperature of the cold side, or both.
Okay, so pretend this is your car.
I mean, imagine you get different efficiency numbers based on whether or not you're using something that's really, really cold. So it really just has to do with how cold your absolute zero is. So if you're using absolute zero as the statement of cold, then it's probably perfectly efficient. But if you're using something that's already hot, well, then you're going to start losing that perfect efficiency. So I guess that would be the real argument. is that built into that mathematics is some reference point that's already way above absolute zero.
Your insurance will pay for another one, right? Well, if you have a standard pump.
Lord Kelvin learns of Carnot's ideal heat engine and realizes it could form the basis for an absolute temperature scale. Imagine that the gas is allowed to expand an extreme amount, so much that it cools to the point where all the gas particles effectively stop moving. Then they would exert no pressure on the piston, and it would take no work to compress it on the cold side, so no heat would be lost.
I don't even know about any of that crap being any kind of truth either. I don't even understand why the piston's going this way when it's cold, so I don't, frankly, I don't even get what he's doing here. This animation doesn't seem to be showing the fact that as you're going colder and colder and colder, the atoms are getting closer and closer and closer to each other. The electrons and protons and everything's getting, the atoms are shrinking essentially. You're contracting the exertion on all surfaces. You're creating an absolute vacuum. Why wouldn't that vacuum be very fast and very real? So I don't know what this is.
This is the idea of absolute zero, and it would make for a 100% efficient engine. Using this absolute temperature...
So there, I was absolutely right. So that's pretty funny. Yes. Okay. I mean, it's funny in a lot of ways. Well, anyway, my critics could say, "Oh yeah, well, it could happen one time a day." He's absolutely right. But I predicted what he would say, right? So, you want 100% efficiency, you have to start with zero temperature. You can't start with some already heated object.
Temperature scale, the Kelvin scale, we can replace the amount of heat in and out with the temperature of the hot and cold side respectively, because they are directly proportional. So we can express efficiency like this, which we can rewrite like this. What we have learned is that the efficiency of an ideal heat engine doesn't depend on the materials or the design of the engine, but fundamentally on the temperatures of the hot and cold sides. To reach 100% efficiency, you'd need infinite temperature on the hot side or absolute zero on the cold side, both of which are impossible in practice.
Yeah, so obviously you don't go for either one of those. You just go for as cold as you can get because that's the one that has a real bottom. The infinite thing is ridiculous, okay? So let's not even bother with that. So just go for the cold side, and the closer you get to the absolute zero, the better. So just try to go colder.
So even with no friction or losses to the environment, it's impossible to make a heat engine 100% efficient. And that's because to return the piston to its original position, you need to dump heat into the cold bar, so not all the energy stays in the flywheel. Now, in Carnot's time, high-pressure steam engines could only reach temperatures up to 160 degrees Celsius, so their theoretical maximum efficiency was 32%, but their real efficiency was more like 3%. That's because real engines experience friction, dissipate heat to the environment, and they don't transfer heat at constant temperatures. So for just as much heat going in, less energy ends up in the flywheel. The rest is spread out over the walls of the cylinder, the axle of the flywheel, and is radiated out into the environment. When energy...
well, regardless, obviously the source is incredibly inefficient likewise, all that smoke going out of the stack.
Spreads out like this, it is impossible to get it back. So this process is irreversible. The total amount of energy didn't change, but it became less usable. Energy is most usable when it is concentrated, and less usable when it's...
So this is sort of a nonsense, right? Because the whole reason why we can function is because of a bunch of tiny discrete energy that has liquefied our environment and made it possible for us to swim in it. And we couldn't swim in it if it was all frozen. So again, just nonsense. There's no rule here. There's no law here that anything has to be a certain inefficiency or any of that kind of crap. And it's just about what we call useful. It's very useful for us to blow things up, so dynamite's very useful, okay? So yeah, things exploding is very useful for us, okay? So things with stored energy, tiny molecules we can carry in our suitcase and blow up the world. Yeah, very useful. But that doesn't have anything to do with what does nature think Nature doesn't care about any of your use standards, and its definition of work is more direct. It's just momentum.
Spread out. Decades later, German physicist Rudolf Clausius studies Carnot's engine, and he comes up with a way to measure how spread out the energy is. He calls this quantity entropy. When all the energy is concentrated in the hotbar, that is low entropy. But as the energy spreads to the surroundings, the walls of the chamber and the axle, well, entropy...
It just means you converted it into the little bits. So that's all there is. There's little bits of energy in the universe, and you can store them, period. And you store them by trapping them between pieces of matter. So electrons and protons store a bunch of energy in their configuration in an atom. And it's just little bits bouncing back and forth between the electrons and protons, and it's controlling the electrons and protons and keeping them in association with each other. And if I break that atom, then I'm going to release all those little bits. That's heat. The little bits are essentially the real core of heat. Heat is, to move an atom, you have to push the atom. And the only thing that's going to push the atom is basically the discrete bits of heat. I mean, push the atom without you kicking it with your foot. So if the atom's going to move by being hit by smaller things versus being hit by bigger things, and that's all you're really saying. But yes, it's all, the real motion in the universe is just the little tiny bits of force, and the only thing they hit is electrons and protons. So if you just reduced it to that simple point, and then electrons and protons clump.
P increases. This means the same amount of energy is present, but in this more dispersed form, it is less available to do work. In 1865, Clausius...
And so again, I'm just going to say that whole sentence, less available to do work, is unscientific, because the definition of work just has to do with what we find useful. Everything is work. Every bit of momentum, every bit of everything is all work. We're just classifying a certain kind of motion as useful and calling all the rest of the motion unuseful. That's not science.
Summarizes the first two laws of thermodynamics like this. First, the energy of the universe is constant. And second, the entropy...
So let's understand, Descartes already said that 200 years earlier. He already said the energy in the universe is constant. He already said God poked it. It's poked. It's now in the thing is moving, and it just keeps moving. It just keeps migrating from one place to another. The energy just keeps moving from one object to another object to another object to another object, and in these little discrete different forms, you could argue. So when all the energy is moving in the same, when all the little bits are moving in the same direction, we'll call that a laser beam or something. But it's just heat, frankly. It's just a form of heat that's all going the same way. When the heat gets dispersed and is shooting all over the place, well, then we call it heat. But it's still heat when it was in a laser beam.
Of the universe tends to a maximum. In other words, energy spreads out.
So this idea that it tends to a maximum is completely opposite to what we see the universe doing, which is creating clumps of burning matter, sending little bits out. So how did it clump? It clumped by a perfectly natural process of the universe, obviously. Obviously, the universe is just as happy clumping as it is declumping. So it's kind of silly to say it tends to, when there's no evidence that that's what it tends to do. For 13 billion years, it's apparently done the same thing of, suns burn and then they burn out and then they start over again, and you just keep recycling the energy. There's no evidence that it's tending to burn out. Now, you could argue that if you were to build the whole universe and then say, well, the whole universe is leaking a bunch of photons, well, then you'd have to say it tends to run out of energy, but you wouldn't say entropy did it. You would just say, well, you let the energy out of the universe. So obviously there has to be some mechanism that keeps the energy in the universe.
out over time. The second law is core to so many phenomena in the world. It's why hot things cool down and cool things heat up, why gas expands to fill a container, why you can't have a perpetual motion machine, because...
So again, it has nothing to do with entropy. That has purely to do with conservation. You can't destroy the energy. So, this is just mixing subjects. I mean, the conservation law, the fact that the energy cannot be created or destroyed, that the motion in the universe, the quantity of motion, as Newton would say, and Newton would say it has to be conserved. That the quantity of motion just moves from one thing to another thing to another thing to another thing.
The amount of usable energy in a closed system is always decreasing.
Alright, so again, bullshit. There's absolutely no evidence that that's happening, okay? Beyond the fact that we're just saying that our systems aren't really closed. That's all you're saying. So if your system isn't really closed, it's the only way it can lose energy. Somehow it has to be in some way or another not closed. If it's closed, you're not going to change it. If you put electricity into a battery, well, if you put the battery in absolute zero, it's not going to lose any of its energy. It's not going to leak it anywhere. It's going to be a real closed system. The closed system is going to lose a damn thing. So again, it doesn't make any sense. There's nothing in a closed system that says I have to turn everything into little bits. Because obviously the clumping rule exists. The clumping gravity is a real thing, and it's going to force the things to clump. And when they clump, they're going to store energy. They're going to merge their energy.
The most common way to describe entropy is as disorder, which makes sense because it is associated with things becoming more mixed, random, and less ordered. But I think the best way to think...
Yeah, it's just baby talk, frankly. So I'm sorry. I mean, it really is. You're breaking things into little pieces. That's it. And obviously, once you break them into little pieces and swirl them around, it's going to be really hard to figure out how to put that back together again.
About entropy is as the tendency of energy to...
But the Earth will do it, right? I mean, I throw something on the ground, it decomposes, and you can see it. The fact that you can watch it decompose. You can watch shit go into the air, and you can watch it evaporate, and you can watch shit to get eaten by bugs. You can watch it happen.
To spread out. So why does energy spread out over time? I mean, most of the laws of physics work exactly the same way, forwards or backwards in time. So how does this clear time dependence arise? Well, let's consider two small metal bars, one hot and one cold.
Oh, he's going to do some kind of relativity crap now. It's just going to be terrible, probably. Just awful. Just a second, please. I think I'm back.
For this simple model, we'll consider only 8 atoms per bar. Each atom vibrates according to the number of energy packets it has. The more packets, the more it vibrates. So let's start with 7 packets of energy in the left bar and 3 in the right. The number of energy packets...
So we could just say the amount of momentum stored. We could call these springs. The atoms are little springs, and we're just saying that we've stored a certain amount of heat into this molecular structure. But this is really... This isn't a very good way to illustrate it, frankly.
Packets in each bar is what we'll call a state. First, let's consider just the left bar. It has 7 energy packets which are free to move around the lattice. This happens non-stop. The energy packets hop randomly from atom to atom.
Oh, whatever. So this is just all crap they made up, and it's their way of describing the idea that the energy is mobile inside of a substance. But frankly, it really doesn't have to be. It's stored in the discrete creation of an ion. So there's, batteries completely run on ions being created. So, I mean, you could, this idea that the ion is moving all over the place or some other kind of crap, it's just that crap.
Giving different configurations of energy, but the total energy stays the same the whole time. Now let's bring the cold bar back in with only...
All Alright, so this is just crashing a 7, something going 7 miles an hour into something going 3 miles an hour. That's all it is.
Only 3 packets and touch them together. The energy packets can now hop around between both bars, creating different configurations. Each unique configuration is equally likely. So what happens?
The total has to be the same. So that's all you're saying, is that the total amount of energy in this system has to stay the same. So the 3 and the 7 become any one number that adds up to 10, because you're just conserving the momentum.
If we take a snapshot at one instant in time and see where all the energy packets are. So stop. Look at this. Now there are 9 energy packets in the left bar and only one.
So this is all made up, right? Like anything ever does that. So there's no evidence that this happens, like something automatically becomes very positive or very negative, that it's switching its state all over the place. There's no evidence that's happening. Bullshit.
1 in the right bar. So heat has flowed from cold to hot. Shouldn't that be impossible because it decreases entropy? Well, this is where Ludwig Boltzmann made an important insight. Heat flowing from cold to hot is...
These generalizations are just useless. You know, to compare cars to atoms to electrons, they all have different rules they're functioning in. The universe of the electron is different than the universe we're in, obviously, in the sense that in every... I mean, it takes me forever, from an electron's point of view, to even utter a word. One word is an insane amount of interactions it's having with the universe. So, you know, on time scales, size scales, and then loss scales, they're very different. The electron is a charged object. It's living in a world of charge. It's not living in a world of this crap.
It's not impossible. It's just improbable. There are 91,520 configurations with 9 energy packets in the left bar, but 627,264 with 5 energy packets in each bar. That is, the energy is more than 6 times as likely to be evenly spread between the bars. But if you add up all the possibilities, you find there's still a 10.5% chance that the left bar ends up with more energy packets than it started.
Right, if this even happened. If this was the rules that the universe functions on, which probably it isn't, because none of these objects can become that imbalanced and stay together. Atoms can't become completely unbalanced. The electron can't go to Venus and then the electron works just fine. I mean, the atom stays stable. I mean, so this is just all kind of not very relevant.
So why don't we observe this happening around us? Well, watch what happens as we increase the number of atoms to 80 per bar and the energy packets to 100, with 70 in the left bar and 30 in the right. There is now only a 0.05% chance that the left solid ends up hotter than it started. And this trend continues as we keep...
This just means, okay, I start off with a penny and I'm flipping it and it has heads and tails, and then I start adding, okay, sides to the heads and tails, that yes, it becomes a lot less probable that I'm going to go heads to tails. I mean, yeah. Duh.
Keep scaling up the system. In everyday solids, there are around 100 trillion atoms and even more energy packets. So heat flowing from cold to hot is just so unlikely that it never happens.
Energy packets. He never told us what this energy packet was. Is that a photon? What the fuck is an energy packet? Shit.
Think of it like this Rubik's Cube. Right now, it is completely solved, but I'm going to close my eyes and make some turns at random. If I keep doing this, it will get further and further from being solved. But how can I be confident that I'm really messing this cube up? Well, because there's only one way for it to be solved, a few ways for it to be almost solved, and quintillions of ways for it to be almost entirely random. Without thought and effort, every turn moves the Rubik's Cube from a highly...
Yeah, that's right, but if your turns are consistent, that is, you turn it to the right and turn it, and turn it to the right and turn it, then you can undo it pretty easily.
unlikely state, that of it being solved, to a more likely state, a total mess.
Moving this summer? Join the 6 million families who discovered a smarter, more flexible way to move with Pods. Save up to 30% off until July 10th.
So if
It's actually an interesting commercial just because I used Pods when I moved. And, it was wet at the one location, so they had a hard time getting the pod, out of the driveway because it was a gravel driveway and it was wet. And then when they brought it, the thing is 12 feet across and the driveway was only 9 feet, and so yes, it was all a bit of a complication. They broke one of their little wheels and stuff, but actually it was a pretty good service, frankly. It works pretty good, but you got to make sure you have the right ground for it.
the natural tendency of energy is to spread out and for things to get messier.
So it really isn't the natural tendency. I mean, it's clear that nature all the time is making sandcastles, all the time it's making hard rocks, all the time it's making all this stuff. So there's no point in saying it's its tendency to declump, when clearly it has a huge tendency to clump. So I guess I'll leave it there. I mean, it's just wrong to say it tends to go mushy, when obviously the universe is tending to go unmushy. I mean, into clumps. I mean, it's just that simple. Yes, things that are clumped will eventually declump. Yes. But clearly there's another mechanism that's creating the clumps. So it's just stupid to say it's tending towards declumping when it's clearly creating clumps all over the goddamn place. So anyway, sorry. It's just, I think it's not fair to the facts. That's all I'd say. It's not a very good description of how the damn thing works. And we'll leave it at that. So, till the next time and such, and so forth and whatnot.